Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm going to tell you, this is the work that I've been involved with, say, for 5-6 years, and it's with a number of people. Some of maybe, so if many of you are new European researchers, maybe some of these names might be familiar to you at universities near you. In particular, this is work that's joint with Andreas Podelsky and Andrei Rybalchenko.
Can I just mention that Andrei Rybalchenko, I think, is a past scholar in
the
program, so that's perhaps worth mentioning that.
In fact, much of this work was done while he was an intern here. Yeah. So intern, and then he became, so he's had association with us for quite a while. Great, and then much of this talk is based on a paper that we've written that shows up in the communications of the ACM. So if you're interested in this and want to read about it more, you can read about it here. And then if you're interested in much more technical, in-depth papers about this material, then I can send you to our webpage where there are more papers, and you can, of course, always just come chat with me, send me email, whatever. Okay, great. So the area that in general that I work in and a number of us work in is that of formal verification. So the idea is that we want to view artifacts as as mathematical systems. So you might think aircraft software, railway switching, hardware, biological systems. I've worked in all of these areas. And we want to, rather than running the system or randomly testing the system, we would want to instead build a mathematical proof of correctness of the system with respect to some property that we're asking. Okay? And this is a number of advantages. And particularly, when we look at systems that are infinite state, right? So there is no bound on the number of states and the possible number of transitions. Exhaustive testing is not only slow, it's impossible. So really the only way forward if you actually want 100% coverage is, rather than just trying to run it on a bunch of examples, is to do a proof in mathematics and logic that the system respects the property that you're after. So as a researcher at Microsoft, I've been involved for a number of years with people who are in the Windows kernel team. So these are the people who write the Windows operating system, and have worked with them to figure out properties that we would want to prove of the operating system. And it turns out, 85% of crashes in Windows operating system is caused by device drivers. So device drivers are the sort of a plug-in mechanism into the operating system. And what I've been involved in is the tools for verifying device drivers that are in the operating system. So here's, for example, the sort of property we would want to prove of a device driver in Windows operating system. So this says the device driver's event handling routine. So what is a device driver? It's 10 to 15 dispatch routines, we call them. And this is really typical in software, right? You see event-driven software that waits for an event. When the event comes, it has a bit of code that handles the event. That code handles the event and then is ready for the next event. And device drivers are like that. So they handle, various events, like, for example, with the mouse, you'd see mouse movement, or a network packet, you'd see packet coming in. These kinds of events are handled by the device driver. So one of these rules that we would like the device drivers to respect is that they're not supposed to call, they only call KE release spin lock when Urkel equals passive, whatever that means. And it doesn't really matter what it means, right? There's hundreds of these complex rules that, as a device driver writer, you have to follow. Okay. In this case, what it's talking about is the priority at which the device driver is operating. So it's a kernel level thread. It can run at different thread priorities, and you can only call KE release spin lock when you're at certain thread priorities, and that's what Urkel equals passive is talking about. Okay. This is an example of something we call a safety property. So a safety property is a property that if you violate the property, you're going to see a finite trace through your program to the place where it's violated. So how you would see a violation to this property is some code through your device driver where it's calling KE release spin lock, but Urkel is not equal to passive. Okay? Great. And in general, safety properties, they're designed to specify bad things that shouldn't happen. Okay? And before moving to Cambridge, which I moved, I think, 8 years ago or 7 years ago, I was involved in a product group called SLAM. And what SLAM was designed to do was to take C programs, especially device drivers, and prove safety properties of them. Okay? And this is now there's at the time this was quite revolutionary. Now there's many tools. You can go to various websites and pick up tools that are designed to take programs and prove safety properties, and they many of them work using techniques analogous to what you see in SLAM. And I'm not really going to talk about that. Here's another property. So the device driver's event handling routine should always terminate. Yeah? So what you want event handling routines to do is to respond to the event and then eventually stop responding. And if you don't get that, then now you're in pretty bad shape. So for example, the operating system will hang, or you won't be able to close a file, right? And that actually happened to me when I first, so I'd worked on SLAM, I'd worked on verifying device drivers, I was feeling quite happy about my work. I came to Cambridge, got my new machine, started using my new machine for like a week, and then the new machine began hanging. Yeah, and it kept hanging. So over the week, I began working with my friends in the Windows kernel team, and we began looking into what was happening, and we discovered that there was a device driver in the system. The dispatch routine wasn't terminating. So it was going into some state and then hanging forever, and thus wasn't releasing some stuff, and then the machine was hanging. And for that reason, I had to reset the machine. So that's another kind of property we'd want to prove of systems. And this is an example of something called a liveness property. So liveness is the opposite of safety. So liveness, a counterexample or a bug to a liveness property could be an infinite execution, right? So for example, another liveness property is whenever you acquire a lock, you eventually release the lock. And one way to violate that is to acquire the lock and then get stuck in a loop, right? So liveness properties are, in some sense, the opposite of safety properties, and we want to prove them too. And liveness properties, morally speaking, they're designed to show the absence, to show that good things eventually happen, right? Not only do you not do any of the bad things, but you do something useful also. That's what liveness properties are out to do. And there's a funny relationship between liveness and termination. If you can build a termination prover for programs, basically you have a liveness prover for programs. You can reduce liveness to termination. Okay, and so then while here in Cambridge, what I've been involved in is a tool called Terminator, which again takes in C programs and is designed to prove termination and other liveness properties of those programs. So here's the sort of thing, when we run Terminator, this is the sort of thing we're looking at. So this is a bit of code from, well, I'm going to switch, I'm getting pretty warm up here. What is this from? This is from the Mao class device driver. So this is a bit of code that gets called basically from every mouse device driver, and actually turns out every keyboard device driver too, right? And here we see a for loop. So this is in C for loop. We want to prove termination of the dispatch routines and device drivers. So what we're out to do in this case is to prove that you can't go through this loop forever. Yeah? So look at it for a moment and convince yourself that it terminates, or maybe it doesn't terminate. Yeah? Some questions are probably coming to your mind, like what's going on with entry, right? So what's happening here is that entry is initialized to some data structure, and then this is a for loop, so it's saying while entry is not equal to this thing, then do this. Yeah? Oh, and then there's all this other code that's doing stuff with entry. So when trying to prove termination, questions naturally arise about like, oh, we see data structures. What kind of data structures are they? Can we find some sort of measure that shows that we'll eventually leave this loop using these data structures? And that's the kind of problem we're trying to solve in Terminator. Okay? Great, and we'll come back to that. So what I wanted to do in this lecture today was to give you kind of the basics. So what happened in termination proving is that there was a little bit of work in the, say, 30s and 40s, and then the topic really died out. And then about 10 years ago, now there's suddenly a big burst of work again. And so a lot of advances have been made in termination proving. Where now, with tools that we have available to us now, actually we can do quite a bit with regards to termination. Whereas before that, it was totally hopeless. So I'm going to tell you, yes, please?
Yes, I was thinking that this problem is just an indecidible problem. No?
That's right, yeah. It's exactly, that's the question. So that'll come up in a moment. So the problem is that this problem is it's called the halting problem, right? It's a very famous problem, actually proved by Turing here in Cambridge, that the problem is undecidable. So it was one of the first proven undecidable problems you actually can't solve with a computer. So there's obviously some sort of mismatch, because here I am saying we're going to prove programs terminating, and then we know that the problem is undecidable, but we can get around that problem just a little bit. So I'll show you in a moment. Okay, so Turing proved that this problem is undecidable, but he also gave us the recipe for proving termination. So there's some subtlety in there, yeah? So this is a little clipping from his paper, 1949, on how to prove programs terminating. It's called checking a large routine. I think he meant like bubble sort or something. Like, it's not a very large routine, but anyways. What I'm going to do is I'm going to read this to you and show you some pictures to show what he's saying. So he's saying, so here we are, we're trying to prove termination. What you need to do is you're trying to verify that the process comes to an end. We need to be assisted by the programmer who gives us an assertion that needs to be verified. And this may take the form of some quantity which should decrease continually until the machine stops. And to the pure mathematicians, remember that the forefathers of computing were mathematicians, this is an ordinal number. Okay, or AK, well-ordered set. So what's he saying? So he's saying programs are represented as transition systems. So you have a pre-state and a post-state, and R is the relation that says, oh, you can go from the pre-state to the post-state in the machine, right? And then we can say, oh, what are all the states that are reachable in our program? So we can go from some state here to some other state. And here we have a little bit of non-determinism, so maybe the user's entered in something, or maybe in a concurrent system, the schedulers decided to go this way or go that way, etc. And we can talk about what is the graph of all the states that are reachable, and what are all the transitions between all the states that are reachable. Okay? And for infinite state systems, this graph is going to be infinite. So what Turing is telling us to do is he says, find a structure-preserving map, and that's a technical term. I'll say a little bit about what that means, such that into a well order. Okay? So he's saying, hey, list all the numbers. So this is like 5, 10, 20, 35. And if you have a mathematical background, then you'll know what the ordinals are. You might know what a well order is, and that's great. And if you don't worry about it. Just think the natural numbers, 0, 1, 2, 3. The ordinals are a lot like the natural numbers, but with a lot of extra stuff in there. Okay? So Turing is saying, take a well order, say the natural numbers if it works, maybe, or some other well order, and pick out for each state a number. So here's the state. Now we're going to define this function f, which for every state picks out a number. Okay? And we have to do that for all of them. Okay? And then what he says it has to be structure preserving. So what that means is, if we take a transition from some state to another state, then when we map with our function over to the numbers, the first number needs to be greater than the second number. Okay? And that's all we have to do. So we find a well order, say the natural numbers. For every state in the system, we pick out a number, and then we just make sure that whenever we take a transition, we're going to a lower number, and there's some conditions on the numbers, like it can't be the reals. You can't go from like 5 to 4.999999. You have to go from, say, 5 to 4. Yeah? And it has to be the natural numbers, for example, there's going to be a least number. So there's a few conditions on the numbers that we're picking, but they're kind of the natural thing. I'm going to introduce a little bit of notation because we're going to use this a little bit in the talk. So what he's saying is, R is your transition relation of your system, and show that it's a subrelation of the lifting of f when you use greater than. So basically this relation here is, take your states, map them via f, and then ask if the one result is greater than the other. And make sure that that relation is greater than your original program. Okay? And if you can do that, you've proved program termination. For those of you who know set theory in the crowd, the lifting of f is just the set of pairs of states, s and t, such that you map via f on both s and t, greater than holds. Great. And that's basically the state of the art until like 1995. Okay? That's kind of all we knew how to do. So if you wanted to prove program termination, on the whiteboard, you would kind of do that kind of thing, right? You would say, oh, my program does this. So then you'd come up with a map in your mind. Oh, it's the map that maps all these things to all these other things. And then you do a little proof. You know, your professor's watching. Oh, okay, I got it going. Yes, we've proved termination. And that's about all you could do. And it was remarkably not automatic. There were really no tools that were available. But a couple of new things have happened, and now I'm going to tell you about what those are. So if you look at the difficulties of proving program termination, two things arise. Okay? There's two things that are really nasty, and this comes back to sort of your comment. First problem. Okay? Imagine that your grandmother is really, really good at finding these mappings. Yeah? We call them ranking functions. Yeah? She's like fantastically smart. So you always can just call her and get an F whenever you need it. Just proving this inclusion, that R is less than the lifting of F, is undecidable. Okay? So there is no procedure that with 100% reliability can in a finite amount of time tell us whether or not R is less than the subrelation. Yeah? Problem number one. Problem number two. Imagine that checking this inclusion is decidable. So imagine that you're really, really great at solving that problem. Still, finding an F is also an undecidable problem. So it's actually undecidable in some sense in two ways. Okay, so that's the problem. And I guess the real change that I've seen in my career in computer science is that when I was studying computer science, everything that was MP or undecidable was like infected. You shouldn't touch it. You should never think about it. And nowadays, with some work on SAT solving, SMT solving, the tool work on SLAM that I told you about, this work here, now the general view, and it's increasingly becoming true, is that only the undecidable problems and only the MP problems are interesting. Everything else is boring, right? Especially in terms of research. So if it's linear, like why are you even worrying about it, right? And that's the change that you've seen, say, in the past 10 years. Okay, so I'm now going to tell you how to sort these two problems out. Okay. So when I finished my PhD, my professor told me you should always make one slide that's impenetrable so people think you're really smart. Yeah, and that's this slide. So we'll struggle along anyways. This is a slide that's indicating why it is that even checking the inclusion is undecidable. So when I said, oh, let's just build the transition relation, what is that? Oh, that's actually a little bit more complicated than you might think. So really, it's U, which is like the update relation. It's saying, hey, you're in this line of the program, execute this command. You're in this line of the program, execute this command, with only reachable states allowed, right? So that's saying, so it's the update relation, but we're going to mask out unreachable states. So U star, that's transitive closure, reflexive transitive closure, when starting from initial states. This U star I, that's the set of reachable states. All of the reachable states in your system is in U star I. U star I cross U star I is a relation that goes from any reachable state to any other reachable state. And then we mask away all the states that aren't reachable with intersection. And that's what R is, yeah? And computing, this U star I is not computable. So we're already in trouble, okay? So what we actually have to do in practice is to find invariance. So Q is an invariant if it's some set of states that's larger than the set of reachable states. But often Q is something that's really easy to express. It's like all states where x is less than y. And then you prove that x is less than y in all reachable states, and then use Q as the invariant when trying to prove termination. Okay? So we'll skip there. So what we can do typically is find some Q, which is an invariant, and that's the undecidable part, one of the undecidable bits. And then, now it's pretty easy, because now we can check that R prime, which is some abstraction, which is maybe larger than the original R, is still less than the termination argument. Okay? There's some terms I could throw out, things like well-founded. Program is terminating if its relation is well-founded. And then we can say things like, oh, if this relation is well-founded, then any sub-relation will also be well-founded. And then because this is always a well-founded relation, then this is well-founded, and therefore this is well-founded, thus R terminates. But maybe that means something to you, maybe it doesn't. It's not crucial. Okay? But in practice, and this is what was really tricky, say 15 years ago on the whiteboard with your professor staring at you, it was often really tricky to find the invariant. Yeah, so he said, okay, prove this program terminating. It has some massively complicated stuff going on, and you're like, you see that x is going down, but x is going down by y, and what's y? What's the value of y? And you look all around, you can't figure out, maybe is y always positive? I don't know. And you have to, let's try and prove that y is always positive. Yeah? So that's the tricky part. But the amazing thing is that nowadays you can just go to basically, any corner store and get a tool which can automatically compute a queue for you pretty reliably. Yeah? So you go, Google some stuff, look up things like BLAST, Absent, SLAM, various other kinds of tools. There's going to be some tool you download, you pipe it together with like Perl scripts or something like that, and now you have a tool that finds your queue automatically for you. Okay? Amazing. So problem sorted. Yeah. So basically what I'm saying is that problem used to be a real problem, but now there's papers, and SLAM is one of the tools, but there's many papers that shows you now effectively how to solve this problem. Second problem, it's hard to find a ranking function, or hard to find one of these mappings. Okay. So there, what's happened, and you see this in the literature in three or four different places. Everyone suddenly decided, oh no, Turing was wrong. Let's go for a different strategy. Sort of change the strategy just a little bit. So rather than finding a single ranking function or a single mapping like Turing told us to do, what we're instead going to do is find a finite number of them. And then, to make sure the whole thing is sound, and for those of you who are into sort of mathematical proofs and so on, there's a little question of soundness, so you have to prove something slightly different. We're going to prove that the non-reflexive transitive closure of R is less than the union of these relations. So basically, we can, from just little parts of the program, find the termination argument that we think should hold. We can throw a whole bunch of these into a big soup. I can throw a big bucket of termination arguments. And then so long as this inclusion holds, we're done. And actually, it doesn't matter if you chuck in extra stuff, right? It's great. So this is fantastic for automation, because what we can now do is take little slices of the program and ask, why is this little slice of the program terminating? Oh, okay, that's because X is going down. Okay, we'll throw that into the soup. And you ask about another slice, and you just keep doing that. And then you keep asking, does the inclusion hold? And then when the inclusion holds, then you're done. Okay? And the soundness of this is based on something called Ramsey's theorem, which is a theorem that's quite old, from the early 1900s. Okay? There are some problems, and I'll tell you about the problems. Okay? So basically, in the old style, Turing style, he said, find one function and make sure that whenever you take any transition from a state to another state, the pre-state, the number you choose out in the beginning is greater than the number you choose out in the later. Okay? What that R plus means is that we're no longer just considering one step. Now we're considering any number of steps. So at R plus, it's R non-reflexive transitive closure. So if you know what that means, then great. And if you don't, I'm going to show you with pictures and just take away the sort of moral story. Is that now we're not considering just one step. It has any number of steps. So for any state that's reachable in your system, and then any other state that's reachable from that state, we now need to ask, does F hold, or G hold, or H hold, right? Does F map to two numbers where one is greater than the other one? Or does G map to some number that's greater than the other one? Or H? Okay? And we have to do that for every unrolling of the program, every two reachable states, where one is reachable and the second one is reachable from the other one, which sounds completely mad, right? Because with infinite state systems, this set is I mean, it's infinite, but it's, mind-boggling, right? It's not only infinite, it's mind-boggling, right? You're taking two states from an infinite set and then asking all possible finite sequences between them. And now you're asking, for all of them, does F or G or does H hold? Okay? But again, there are tools that solve this problem now. Okay? So here's a little, this is basically the Terminator algorithm. And the very first version of Terminator really was a Python script that called two tools that I downloaded off the internet. Okay? So here we go. What you do is you start off with the empty termination argument. So the empty termination argument says it's no states are related. There is no termination argument. Okay? And then you ask, does that inclusion hold? So basically it's saying, does your program never make a step at all? That's probably going to fail, and you're going to find a step. Yeah? And we ask one of these off-the-shelf tools of that question. So the inclusion question we can hand to another tool, and I'm going to show you that if time permits. Great. So if the inclusion holds, then we're done. If the inclusion doesn't hold, so if the inclusion check succeeds, we've proved termination. If it fails, then what we get is a path through the program. And that's a little slice through the program. Right? And we're going to ask, oh, what about that slice? Is that terminating? Could you visit that slice of the program forever? Oh, no? Okay. Then find a ranking function, and add it in. Otherwise, now we found a counterexample to determination. Okay? And it turns out that there's also some work in the literature that for very simple paths, so basically slices of programs, and for a very simple class of argument, these ranking functions or these mappings that we're trying to find, for a very simple class of them, they have to be expressed in linear arithmetic, the question is actually now decidable. So and also very, very fast. So you can reduce the whole problem to an SMT solver and call that tool, again, off the shelf. So my termination prover now is something like 10,000 lines of code, of F# code, but basically it's calling, much of the work is actually the reachability prover or the SLAM-like tool, and the termination part is probably 1,000 lines of code, and then it calls something called Z3, which is an SMT solver for Microsoft. Okay. Anyways, and if all of that fails, then we just go back. Like if we find a new ranking function, we put it in, we go to the beginning and iterate that process again. So we start off with the empty relation. We ask if that holds. We call a tool, say, does that hold? Okay, no, it doesn't. So we get some counterexample. Then we ask, can we find a ranking function, but just for that little slice of the program? Okay, we can. Great. This is in Terminator. It's based on something called Farkas lemma, which is again an old theorem. We find the ranking function, we add it in, and we just iterate this process until we find a real counterexample or we find a proof. Okay, and that's how Terminator works. Okay, and that's that problem sorted out. So now we're done. Now let me show you a little bit about how we do this reduction, how we ask the other tool to check the inclusion, and then also we'll look at a couple of examples. Okay. So the question is now, if I get a tool that proves safety of programs, how do I reduce the checking of this inclusion to safety? Okay? And I'm going to make the following requirement, which is a practical requirement in terms of tools. There's many tools available, and they all have the following characteristic. What you can do with them as a minimum is you can ask, is this line in the program reachable? Okay? And those tools, those safety provers will say, no, it's not reachable, and I've proved it's not reachable. Or it'll say, yes, it is reachable, and here's a path to that location in the program. Okay? So you can point at line 25 and say, can you ever get there or not? And they'll say, no, here's a proof. Or it'll say, yes, you can, here's a path to that location. And we're going to encode the checking of that inclusion as a reachability problem for a safety prover. So imagine that we have some termination argument already, and we're trying to prove that this little loop terminates. And we're going to do one thing to make our lives easier. We're going to prove that we can only visit this location infinitely often here. Okay? And if we do that for every line in the program, or you can actually do something a little bit smarter, if you prove that every line, if you can't visit that location infinitely often, then you've now proved the program terminating, and that's what we're going to do. It's a little bit easier to understand if you think of it that way. Okay? So we're just trying to prove we can't visit this line here infinitely often, right after the bracket. Okay? So here's, and then we have some termination argument. It's T1, T2, T3. It doesn't really matter what it is. It's some relation. It's talking about pairs of states. Okay? So here's the program that we now can pass to one of these existing tools. So these existing tools, for example, we can ask, can this assert ever fail? Yeah? And these existing tools will either say, yes, it is possible for it to fail, and it will show you a path where T2 isn't true, T1 isn't true, and T3 isn't true. Or it'll say, no, it's not possible for the assert to fail, and it'll find a proof. And this assert fails if and only if that inclusion doesn't hold. Okay? That's how we do it. So I basically do this little program transformation on I take your program, I'm trying to prove terminating. I find a termination argument using the methods I told you before. And now when I want to check the inclusion, I do this little program transformation, build this new program, and then call basically an off-the-shelf existing tool to prove that assert can't fail. And if the assert can't fail, I've now proved termination. Okay? And I'll give you a taste of how it works. Basically, there's a new variable called copied. It's initialized to 0. And what we're going to do is we're going to allow this program to run. And at some time, and this is, if there's one thing that you walk away knowing from this talk, let it be the following thing. We use non-determinism in this really powerful way. Okay? If you ever do proofs of programs, ever do proofs of systems, mathematical proofs, non-determinism is your greatest friend. Okay? And that's what we're going to do here. So we're going to allow the program to run, but any time non-deterministically, we are going to copy all the values of the variables and put them into some other variables and store them away. Yeah? And because we do it non-deterministically, that allows us to say that we now have any previous state. Yeah? Okay, so I imagine that copied is 0. We go for a while, we do something, we hit this while, we come here, we say, hey, is copied equal to 0? Yes, it is. Okay, if star, and star is non-determinism. This is never a program we're actually going to run, but this is a program that we're going to prove, right? So we don't have to worry about how to implement non-determinism in a runtime. We just have to worry about how we're going to prove this program. And it turns out for doing mathematical proofs of programs, non-determinism is extremely easy to deal with. So here we are, non-deterministic choice. Let's not take the choice now. So come here, and then we'll come here. And then we go off and do F, we go off and do G. And maybe we get stuck in F and G. It doesn't matter because we'll prove that you can't visit locations inside F and G infinitely often separately. Imagine we come back. We're back here. Oh, x is less than y again. Okay. Copied still equal to 0. Great. Let's take the choice now. So now we copy x and y into this little associative array I have, and then set copied to 1. Now we've copied the values of the variables. So x and y are now stored away. Okay. Okay, we come out, we go around, we go into F, we go into G again. Maybe we come back out around. Okay, now copied is equal to 1, so we're not going to go there, but we're going to go here. And now, if we've written T1, T2, and T3 appropriately, we can now ask questions about the current state and the old state. And so that's how we check this R+. So it's the current state and any previous state we can ask, what's the relationship between them? So we could ask, for example, is the function f, like, does x always go down from now and any previous state? And if it's not true, then that assert will fail. And so that's how we do the program transformation. Okay, I've said that basically. So let's look at some examples. Okay, so usually when I give this talk, half of the audience is extremely abstract and they're really unhappy with this section, and about half the audience hasn't followed a word I'm saying, and this section makes them feel a lot better because they're like, oh, okay, now I see what you're saying. So here's a little C program, and P is a pointer to an integer. It's pointing to the address of x. And the question is, does this program terminate? And this is the interactive part of the talk, so now I'm going to ask you questions. Yeah? And I expect answers, and I'll pick randomly, so think about it. Yeah? So the question is, does this program terminate? Oh, and by the way, integers, and just to make life interesting, we're going to assume that integers are of arbitrary length. So there's no overflow. Right? It's not 64 or 32-bit vectors. We're talking about arbitrary length integers. Okay? So, and the other thing is, sorry, I've switched notation a little bit. Non-det, that's non-determinism. So that was star before. Okay. So you answer the question now. Scarlett?
Volunteers? Yeah, I actually forgot one.
Well?
Could non-det assign a value greater than 100?
I could, yeah. Yeah, so the thing is that if non-det assigns a value greater than 100, then you're going to go into the loop, but P aliases X. So this star P plus plus actually makes, if it's greater than 100, then you won't go in the loop and it terminates. Sorry. So it terminates in that case. But if X is less than 100, then you are going to go in the loop, but now X is going to get increasingly towards 100. Every time around the loop, X is going to go up a little bit. And for that reason, it does terminate. So the program does terminate. Here's the termination argument we found in Terminator. So this is the relationship between the current value of x and the old value of x, some previous value of x. And what this is here, I've pushed this around. It's saying the Turing's ranking function in this case, and this is a simple case, is minus x. So the function is take whatever the value of x is and negate it. And that, if you look at that value, it's always going to go down. Another way to think of that is it's saying, hey, when you're at line 6, x is always, just after you've gone into the end of the loop, x is always going to be less than 100, and x is always going to be greater than it ever was before. And so for that reason, the program terminates. Okay? And how we found that is we started off with the empty termination argument. We ran this tool slam, actually. Slam found a counterexample to the assert that I've encoded in it. Then we looked at that counterexample, and the counterexample is, you come in x is under 100, you increment x once, and you come back around. And we said, oh, in that case, actually, x goes up. So the negation of x goes down, and that's our ranking function. We put that in here, so it's saying that x is above some bound, and minus x is above some bound, and x is always going up. We add that in, and then the assert doesn't fail the next time around, and then we're done. Yes?
Okay, so as you explained before, you are making like one single test for one iteration, and you say that it's going down, and
Yep.
you infer that it's always happening, so you get the function.
Yep.
But in the previous example you shown, there is another function being called, which you don't probably know how it's behaving, and then you cannot make this into
We do, because what we do, in the case where it's the other function isn't terminating, then we'll catch that later when we're checking the same condition for it. And then if it does terminate, then whatever our magical proof system, however our safety prover already knows how to handle that. So either way, we're okay. So if there was some, the question is, what if you have some procedure call inside this loop? How do you handle that? And the safety prover, and I'm abstracting away from that, I'll tell you, it's another hour talk. But the safety prover has ways of dealing with that. But if we're worried about if the sub-procedure terminates, then we're going to have to go into the sub-procedure and do similar checks for every while loop, for every recursive call site, for every goto. Okay. Great. Oh, and by the way, so what Terminator did is it figured out that it only needed to do something at line 6. So it really only needed to prove that we don't visit this location infinitely often. I can do Ackermans. Everybody always asks, can you do Ackermans? I can do Ackermans. In fact, it's a recursive definition of Ackermans. If I modify Ackermans and I actually get a counterexample, and the counterexample is going to the right a little bit every recursive call site, and it's this. The cycle is from 11 back to 11. That's not very interesting. Here's a much more interesting example. So look at this program. Same game as before. You know what non-det is. So here non-det is either returning true or either returning false. And here we're assigning x, y, and z to non-det. And the question is, does this program terminate? Yeah, good, yeah. Why?
Because either x is growing or that is...
Fantastic, yeah. See, in the old, what's the single ranking function? That's trickier.
A tuple of minus x and z. X is going down.
X plus minus z?
No, I think it's something like 2. You have to multiply 1. I think it's 2x minus z or something. Yeah. And actually, what's interesting, if you make this x gets non-det, then there is no linear ranking function. It's an example of where you need larger ordinals than the natural numbers, for those of you who know what that means. But no matter what we do, actually here, the same proof works. So this x could be non-det or x could go down, doesn't really matter. But yeah, that's the right way of thinking about it. I mean, it's much easier to think this way. You've already taken on my approach now. So what you do is you just look at every possible path. You say, why does that one go down? And then you just throw the argument in, and then now you're done. You know? So what Terminator did is it started off with the empty termination argument, and it said, can you ever basically get from line 7 back to line 7? Well, you can. One way to get back to line 7, from line 7 to line 7 is to check this condition, take this choice, increment x, come back around. And it said, oh, okay, in that slice, same as before. The negation of x is always going down, or x is always going up. Okay, great. We add that in. Is that enough? No, it's not. Because look, there's a way for x not to go up. That's where you come here, you take the else branch, you actually decrement x and decrement z. So that violates this piece of the termination argument. Oh, okay, well in that case, z's going down. So we just say, oh, look, z's less than it's ever been. We add that in, try again, and that's it. We're done. So that's how Terminator works. Here's a little puzzle. So does this program terminate? Yeah, so it does. It does, and it does, interestingly, if you ignore the context. If you just take this while loop out of the context, it doesn't, right? Because you don't know what y is doing. If y is positive or negative, you don't know. What happened in this case is we found the particular cycle. We found, oh, y is positive in this case, x is under 100, x goes up by y, and we found the same termination argument. The termination argument as before is x goes up. Okay. Now, we ask the safety prover with that program transformation I showed you, can that assert ever fail? And it can't. And to do it, it had to find an inductive invariant. So it found, if you look in the details, you'll figure out that you'll see that it finds an invariant that at location 8, y is always positive, and it proves it. And that turns out to be really crucial. So that's what I meant by the Q, right? That invariant used to be really tricky to find. I mean, it's obviously not very tricky in this case, but in other cases it is. But now, the tools do it automatically for us. We don't have to worry about it anymore. Yeah? And that's kind of the magic. There's tools that, for proving for proving safety, for proving the locations aren't reachable, they find inductive arguments that it's not reachable, and they somehow find them and somehow prove them. And that's via, these days, interpolation. It used to be via something called predicate abstraction, but that's like, now I'm explaining like 20 papers, so I won't tell you about it. But there's really neat techniques in there. Okay. All right, so I'm a researcher at Microsoft. One of the things I do is I look for cool ideas and how they can have impact in the industry. So I try and like make things that work for people who care about them. And so I worked with the Windows kernel team, but in particular I worked with a lot of device driver writers outside of Microsoft who were writing device driver writers. And then another thing I do as a researcher is I publish papers. So we published this paper in 2006, which talked about Terminator. And then what was interesting there is we applied it to Windows device drivers. We found a bunch of bugs in Windows device drivers. Oh, these Windows device drivers, it's interesting. These are not only the Windows device drivers that run in my system, they're also the Windows device drivers that we were giving away as examples of good device drivers. Yeah? And so when you wrote your own device drivers, typically what you did is you copied and pasted and then modified. So these device drivers had been in the system since 1995, right? So a lot of these termination bugs had been around for a long time. And we didn't know about them, and they were propagating as people copied and pasted. And the device drivers are anywhere from 35,000 lines of code to 8,000 lines of code, 5,000 lines of code, et cetera. It's parallel port, serial port, floppy, keyboard, et cetera, et cetera. And then we found some proofs. And then we found some cases where we didn't know. And that's to the problem of undecidability. So the trick with undecidability is to make a tool that when it says yes, you know the answer is yes. And when it says no, you know the answer is no. But when it says it's not afraid to say maybe. Yeah? So you can't answer the question. The halting problem is you have to answer it in a finite amount of time with 100% accuracy. And so long as you're willing to give an I don't know answer, then everything's cool. And you just have to get that threshold down to make it useful for people, to get the number of question marks down to some useful level. And that's where we're aiming. There's a paper in Scientific American about the tool. And then we just started solving more problems. So we handled programs that use the heap, handled programs. This made the tool faster. This allowed us to do all liveness properties. Here we're dealing with programs that have nonlinear termination arguments. Oh, I lied to you. Actually, I was considering only sequential programs, but actually device drivers are concurrent programs. So we had to figure out how to deal with concurrent programs. We did that in this paper. Another paper about how to make it faster. Oh, what do you do when a program doesn't terminate? One thing you can do is you can infer a condition that if it held at the beginning of the loop, then the program would terminate, called preconditions. We have a paper on how to do that. Here we're applying it to these fine-grained concurrent non-blocking programs. So it turns out for a non-blocking algorithm to be non-blocking, it means actually there's a termination, a liveness question that needs to hold. Here we're doing more temporal properties. Turns out in biology they need the same thing. So there's people who build models of biological systems, and one of the big questions they have is something called stabilization, which actually turns out to be pretty much termination with a little twist. So I've worked on that. So what I want to do is to close with a bug. So I'm really interested in proofs, yeah, for tools that say, yes, the property holds even for this infinite state system, but unfortunately proofs don't demo very well. Yeah, because I could show you some massive inductive proof that it found, and it might take 10 hours to find it. and it's not very interesting. So what I'm going to do is show you a bug that we found when the tool failed to find a proof. Okay? And it's in this code that we saw before. So this is from mouse device driver. Okay? And to see this bug, you need to observe that what this code is doing is it's operating over a cyclic doubly linked list. So I've drawn just the forward edges. So here's the read queue, that's read queue, and flink is for forward link. So read queue flink is this node here. So the entry starts off at read queue flink here, and then while entry is not equal to read queue, i.e. while entry is not equal to this node, it increments, so entry gets entry arrow flink, meaning go to the next link, and then do this code here. Okay? So to see this bug, imagine that entry is this node here. So we've gone a little ways. And what we're doing here is we're calling remove list entry. So remove entry list. And what this is doing is it's doing a remove of a node from a cyclic doubly linked list. So it's going to make the previous node's pointer point ahead and the forward node's pointer point back. Okay? So basically we just do some pointer swing. So we'll watch what happens. Oh, see, we just removed it out. Okay? But it still points into the list. Okay? Then we do this. And then look at this. See all these comments here? There's some misspelling in there. I find that often when there's a bug, there's a lot of comments, you know. There's like a little heuristic, you know. When you're fishing, it's like, oh, good waters, you know. I see a lot of comments, some misspelling. That's pretty suspicious already. Because often the programmer doesn't really know why it works, so he's trying to explain to him or herself why it works, and sometimes they get it wrong. Yeah? There's a little bit of an interesting sort of concurrency case here. It comes here. And then what's going on here? This is tricky. So the initialized list head, that makes a new cyclic doubly linked list. So it says take a node that's already been allocated, already mallocked, and make its forward and back pointers point back to itself. And the bad news is that entry and this expression alias. So this is like initialized list head of entry. Okay? So watch what happens to the red dot when I execute this. Yeah? So now entry points to itself because we've initialized it. Yeah? Okay, great. That's bad news because now entry gets entry arrow flink just means nothing. It just points to itself again. And now entry is never going to point to read queue, right? Because it's not reachable anymore. So we're just going to just race along forever on this little empty list that we've just initialized, and we're screwed. Okay, so I have friends that I ask when I find bugs if they're real bugs, and he says yes, it's a real bug. And then, but he makes this point. You don't even get a courtesy crash. Right? When a safety problem occurs, often a program crashes or an assert is violated or something really bad happens. You know, the rockets are launched. Yeah? But in this case, we don't even know we're in trouble. Right? Why not just wait for a few more minutes? Yeah? But you're never going to be able to wait long enough. The system's hung, and you don't even get a crash. And that's actually how traditionally, Microsoft has been finding out about bugs in their system is that the system crashes and it asks, would you like to tell Microsoft about this? You click yes. That information goes to some database, and there's like people using machine learning techniques trying to figure out what the root causes of problems are and so on and so forth. And then we like, oh, these device drivers are causing lots of crashes. And we go to Dell and say, don't buy these device drivers, buy these device drivers, etc. But we weren't seeing those at all. So that's why all these hangs were in the system, and we never knew what was causing them. We just knew people were resetting their machines a lot. Okay, so that's pretty much it. So let me leave you with, now let me tone it down a little bit. Yeah. So I made things seem very, very easy, and I want to give a slightly more subtle argument. So the previous wisdom was that proving termination was impossible. In fact, whenever you talked about it in the old days, people laughed and said, oh, but that's the halting problem, you're an idiot. Yeah? And nowadays, people are beginning to think, oh, actually, termination problem is pretty interesting. And unfortunately, a lot of people think it's actually solved, and it's not solved. Okay? So not only is it not solved because it's formally undecidable, so it will never actually be solved, but secondly, there's a lot that we can't handle these days still. And you see in my research area, you see the literature with lots of papers hammering away at these problems. So I'll just pick a couple of them. Concurrent programs are quite tricky still, or modern programming language features like termination of JavaScript or termination of F#. Another question is infinite state systems that also have bit vectors. Basically, it's easy to do programs with bit vectors. It's easy to do programs with infinite state. It's trickier when you have programs with lists, and bit vectors, so on. So those are in complex data structures, say DAGs and so on. That's where it gets tricky. The other thing is that, so our life, our life is changing. It used to be, so the good thing about this assumption that that anything that was undecidable or anything that was NP was infected and you should never touch it, is that this idea that you could call black box tools to solve problems worked. Yeah? Oh, you have a problem? Oh, you just download this tool from Berkeley and call it, and it will solve your whatever linear problem. You call a compiler, no problem. Compiler will eventually give you an answer. If it doesn't give you the right answer, file a bug. But nowadays, what happens is you download this tool, you encode your problem for it, you call it, and it runs forever. And you're like, now what do I do? Yeah? And so that's the problem, is that black boxing or abstraction, using someone else's tool to solve your problem, becomes much, much trickier when you're using tools that are trying to solve NP problems or undecidable problems. And that's what we're seeing. So it's actually like parsing. You don't need to understand parsing, right? Who cares about parsing? You just call a parser. Parser generator, you're done. But with these kinds of problems, automatically finding inductive invariants, automatically finding termination arguments or arguments of progress, if your research takes you into that area, it's going to be very tricky actually just to call these procedures as black boxes. You're actually going to need to understand how the tools work and adapt them a little bit, right? Because you're not going to be able to encode your problem and call them for a while. Okay, that's a warning.
Alan, how widely are these tools used then nowadays?
There's a termination competition now. So there's like 15 tools, and they're scaling up to increasingly industrial. So industrial application of the tools is limited but happening. And then now there's a worldwide competition with all these people trying to make better termination provers. And then for safety, it's quite widely. So in aircraft, railway switching, et cetera, so you see it quite a bit. I think I just had one more slide. Oh yeah. So there's a web page about Terminator, research papers, more technical lectures, contact details for me. There's the CACM review article, but also you can just send me email and ask questions, and I'm happy to answer them. My job as a researcher is to interface with the outside, right? So if you're the outside, so ask me questions and I'll interface with you, right? So thanks very much.
So questions for Byron? Yeah.
So we talk about aviation technology, where cloud is really important. Obviously, these things are not only, they're also tested. They're not just proven correct. Like, would you say that, for example, kernel drivers are intrinsically harder to test in this way? And that's why we need these kind of tools.
The testing technology is improving also. So there's a line of work in the research about better methods for testing these kinds of programs, and they're also making a lot of progress. The thing is that testing will never give you 100% assurance, so usually a mixture of the two. So these approaches are very heavy duty, and they often take a long time. So in the early days, it would take, for termination of one device driver, it would take 80 hours. Yeah? And then for every liveness property was reduced to a termination problem. So if you want to prove 100 liveness properties of your device driver, it's 100 times 80. That's pretty long. Whereas a testing tool can really quickly find. And so there's a lot of work on really great ways of sort of causing the tests to find the little difficult parts of your code. And so they seem to be making progress too. So it's sort of the two things together. One is really fast at finding bugs, and the other, it will then give you the final thing saying you're now done. Yeah. Oh, and the other thing is that the techniques in a way are combining. So I didn't give a talk about this, but the tools for proving safety nowadays use much more testing methodology, and then they generalize. So they basically do tests up to some level and then somehow magically synthesize an inductive invariant from the tests they've run and then prove the induction, and now they're done. Whereas in the early days, there were other techniques that have basically been abandoned now.
Yeah, I wanted to ask if is any proposal to include all this testing and Terminator onto the compiler itself. So when you are compiling and generating code,
So the history of this area is that, say, in the 60s and 70s, a bunch of promises were made that couldn't be kept, right? So people, say McCarthy, said, oh, you know, in the future, you know, everything's going to be solvable. You know, robots will do everything, and you know, computers will solve all problems. And then people got extremely disappointed because it didn't really turn out to be true. And so what you, and same was true for program verification. So the early papers in program verification were just like, what's the problem? Just verify it, right? And what's happened in the meantime is that people have gotten much more specialized. They're like, oh, program termination or program proving, extremely tricky. So what we're going to do is we're going to find like a class of programs and come up with techniques that work really well for those programs. And we'll just keep chipping away at that problem, keep chipping away. And maybe eventually we'll sort of get to the point where everyone who writes a program for a living, their programs we can handle. Yeah, everyone gets paid like a salary, gets stock options, we can handle them. But then, you know, there's always going to be some mathematician who can write some really incredibly, there's a little 5-line program called Collat's program, no one knows if it terminates or not. And all expressible with linear arithmetic. Yeah, it's 3 and it's like while x positive, x gets 3x plus 1 or something like that. Or if it's divisible by 2, then divide it by 2. And that program, no one knows if it terminates or not. So the tricky bit for rolling these tools out, general purpose, is that everyone's going to get into a lot of trouble. Yeah, they're going to start using these tools, and the tools aren't going to answer, and then you don't really know what to do. So the trick is to find specialized domains where you either have an audience that's mathematically capable of dealing with troubles and helping the tool along, or to choose domains like device drivers or aircraft software or other areas where you can come up with heuristics where it for 99% of the time will work, and no one will even need to know about the techniques underneath. And until we get to the point where they're like they work for all programs, it's probably a mistake to make them available for just all compilers. So it's more like a specialist tool.
About, I mean, you were showing this in this paper, you were applying this technique on the device drivers of Windows.
Yeah.
And some of them, they didn't pass this test, no? So it's like you don't know if it's going, I mean, it's not going to hang or not.
Yeah, exactly.
So,
Yeah.
I mean, my question is it possible in all these cases to rewrite the device driver to meet the expectations?
Yeah.
It's
Yeah.
always possible.
Yeah, and all of them.
So you could, I mean, the
Yeah.
software packager can be assured that it's totally working.
Yeah. So yeah, I mean, once they're fixed, then now your termination proof goes through. So, yeah. And so, I mean, these bugs are kind of interesting to exercise. I think that one, how you exercise it is you move the mouse and pull it out of the USB port at the same time. Yeah. But there's various, like, it often involves concurrency and hardware failure all at the same time. So for example, Zune, which is Microsoft's attempt to be like an iPod, they had on New Year's Day 2 years ago or 3 years ago, all of them hung. And it was because they had a little termination bug in the calculation of the leap year. But yeah, usually once you find them, it's not too hard to fix.
Any questions?
So kind of related to that, what kind of false positive breaks do you see? Like you find lots of things which can't terminate, but if you express it differently, you make it quite obvious that it doesn't.
Yeah, it depends on the application area. So if I'm applying it to really difficult mathematical puzzles written by my friends and enemies, then my false positive rate is very bad. But if I apply it to systems code, 10,000 lines or under, then I'm in pretty good shape these days. And then if I apply it to much more complicated, like the internals of Linux kernel or something like that, then things get pretty tricky. So it depends on the kind of code, and if you're talking about really tricky code, then what you need is someone sort of guiding things along. But in the terms of 100% automation, then if it's sort of systems code written by people who aren't especially sophisticated, then we might have some progress. So, but the story's not written yet, right? So we'll see how things go in the next 5 years or so.
Okay, I think we've reached the end of the afternoon to try and grab Bar if you have further questions. But thank you very much.
Thanks.